Hi, in this series of videos we're going to have a look at C++ as a programming language, some of the features that it has, and also having a look at an introductory level how it actually works underneath the surface. So it is an introduction to C++, but it's one that is intended to really be of help to individuals who have some experience of a higher level managed programming language, something like, say, Java or C#. Understanding C++ and understanding how it works actually will be a benefit in itself, but it will also help in terms of your understanding then of other programming languages. In these first few videos, I want to actually take the time to set out why I believe it is actually important to explore languages like C++ or C. Even if you think, okay, I'm only ever going to be, I'm going to be a C# programmer or a Java programmer, that's what I do most of my developing in. I would argue, and I want to try to make the case, that it nevertheless is very important to have a good grounding, a good understanding of some lower level languages like C, like C++, because understanding how they work, and it can be somewhat painful in terms of understanding how they work, but understanding that actually will help your programming language or abilities in general, not specific to low level languages. So I want to try to sort of take the time to set this out in the first couple of videos. Start off with a little bit of history about C++. It was created in the early 1980s at AT&T. It's an old programming language, and it has evolved and it's changed over the years. And sometimes when languages evolve, for example in Java or C#, and all languages do evolve over time, or rather most do evolve over time, there's different approaches you can take. You can either have an evolution where you then decide to remove or to phase out old language features which you don't think are relevant, or you can still try to maintain or keep them on. C++, by way of its evolution, has generally speaking held to its founding principles, and whilst it has changed, the changes have tended to be in a way where they haven't broken the language as it was in the past. So most modern C++ compilers, you could take a piece of C++ code written in the early 1980s and still be able to compile it today. Because it's an old language, 1980s, it's a long time ago in terms of computing history. It means that it's a few characteristics. I can make the case it's a powerful language, but it can also be quite an unforgiving language. And a lot of the evolution of languages after or from C++ has been trying to improve on it to make it a more programmer-friendly language. But we'll see that as we go through. C++ itself, and if you have a look down at the bottom of this slide, you got a sort of a snippet from really back from the 70s up to about 2000 of some of the programming languages. And you can see from this that there is very much an evolution of languages. So down at the very, very bottom, we have, you'll see C coming in sort of the early 1970s. And actually, C was based on B, the programming language, which you might think was based on A, but it wasn't. There you go. And C actually is still used nowadays, so it travels all the way through. But a little bit up in the early 1980s then, you have C with classes, which turned into C++. So C++ itself is actually derived or based on C, and very closely so. And if we want to understand C++, it's actually useful starting with C initially. And to a certain extent, C is a sort of procedural basic programming language. It's not object-oriented. C++ is an object-oriented language, and it added that additional functionality into it. Indeed, some of the very early C++ compilers, well, all they really did was to take a C++ program, turn it into a C program, and then pass it off to a C compiler. So next few slides, we're going to have a look at C as the foundation, the principles in which C++ itself is based. Just an aside, if you do look down at the bottom, you can see that from C++, or actually from C, you have Objective-C coming off in terms of things that are still used on Apple-based programming. From C++ later through around early 1990s, we had Java. And one of the inspirations for Java was C++. And then C# up around the year 2000, where you have sort of the inspirations of C# coming from Java and from C++ itself. So these are actually quite a closely knit and related family of programming languages. Okay, so C then, the foundation, if you like, of C++. C would be classified as a low-level programming language. Low-level means that it gives a lot of control to the programmer. You're just really one step above assembly language. A lot of good C programmers will have a very accurate feel that if they were to write a line of C, what type of assembly or machine instructions it would get turned into. So it is down very much at that low level in terms of control. And the reason C is still used quite a lot today is for things like embedded programming, where you are down interacting very directly with the hardware and controlling it precisely. And there's still a lot of programming activities which require that type of control. Now, C is early 70s, is older than C++. Back in the 70s, back in the 80s, processors were millions of times less powerful than they are nowadays. And it meant that when you were writing something, you generally wanted it to run as fast as it possibly could. That also applies today, but there was less computational resource in which to actually get done what you needed to get to do. What this means is that C as a programming language, it lacks an awful lot of the safeguards, the checks that modern languages like Java and C# put in. So an awful lot of for example, the compilation errors that you might get when you're doing, say, Java programming, where sort of complaining about you casting or trying to convert one thing into another thing or doing an invalid operation, you wouldn't get those in C. It ignores an awful lot of these types of run checking. That makes it fast. So it's not actually spending its time checking to see if the program's doing anything suspect or dangerous or silly. But obviously, the counterpart of this is it actually makes the program potentially dangerous then. So I can declare an array in C, and if I want, I can access a position outside of that array. I can declare maybe an array of, say, 100 ints, and I want to access the -4th element in it. It'll let me do that. So it doesn't check to see if you're still within the bounds of the array. It's a delightful language for hackers because things that are written in C get to be executed in that. There's little control of it. You can sort of inject or control elements of it. So fast, but fundamentally, potentially unsafe. For C++, it inherits really the strengths and the limitations of C. In C++, and the stuff we're looking at is not really going to be at the class-based level, it's more down at the sort of algorithmic level. You can write relatively low-level code that gets to be run very fast. And one of the ways it'll do this is that there's going to be relatively little runtime checking. It means that the burden of making sure that it runs correctly falls on the programmer. So when we're writing our programs, we have to be very careful that we write them without bugs. And it requires more effort. It's a more painful process. There are likely to be more bugs. They're likely to be more difficult to find. We're going to have to put in that time and effort. In order for us actually to write it safely and to minimize the number of bugs, what we're going to have to do when thinking about C++ or C programming is to have a very clear understanding of how the code that we write, how it actually will get to be executed, what impact, what net outcome will it have. And that's the extremely useful bit that sometimes can be hidden or not as clearly exposed within other languages like Java or C#. A little bit here just about how C++ has evolved over the years, and you can see it going from left across to right. So C++98, this is a traditional old standard C, one of the ANSI defined ones. It has changed over its lifetime. The C++98 is probably the most well-known, well-regarded, well-used, standardized version of C++. There was a small variation to it, C++03, wasn't really any significance. And then in 2011, you have C++11. This was a major revision of C++. And added in a lot of new language features aimed to sort of improve the consistency, the safety of the language. And actually, that revision to C++, it was drawn upon some of the useful features that other languages like Java and C# have introduced. So to a certain extent then, that C++ itself has been evolving to take into account programming practices inherent in Java in C#. So it's improving. At this point, this probably won't make a huge amount of sense, but it will later on once we've gone through the course. These are some of the language features here that C++11 provides. So things like smart pointers instead of raw pointers. We'll look at pointers, and the pointers we're going to look at are just raw pointers. They point to location in memory. The types of reference, sort of indirect pointers that we deal with, say, in Java and C#, they're all smart pointers. They know the types of things that they ought to point to, and are very picky about what it is they can point to. Stack-based scope instead of heap or static global scope. You'll see that when we look at C++, we can choose where we actually get to store our variables on the on the stack, on the heap. Are they global ones, or are they not? Again, for stack-based scope, that's also moving more to the default storage within other languages like Java and C#. STL containers instead of raw arrays. We're going to have a look at raw arrays, just basic chunks of memory that have been allocated. You don't have those in Java, you don't have them in C#. You have defined classes that encapsulate functionality and embed safety. And C++11 recommends that that's what you use. Auto-type inferences instead of explicit type names, robust range-based loops instead of traditional loop termination. Again, other language features. So these are all characteristics, good programming characteristics that really were introduced and strengthened through languages like Java and C# that are now making their way, I suppose, back in formally into C++. Now, it is true to say that in C++11, if you wanted to, you can write code that has much the same range of features and much of the same level of safety as you could write it in C# and Java. You may think, okay, well, swings and roundabouts then, they're all roughly the same, and to a certain extent they are. However, we're not going to look at C++11. I want to look at C++98, the old style C++. And you might think that's a bit of a strange thing to do whenever they've introduced these very obvious improvements to C++, but I want to spend a little bit of time just to try to make the argument as to why I think there's benefit in looking at old style C++. So I said multiple times that C++, they're fast languages. They low level, let you write fast code. I also said it's also somewhat a difficult language as well. There's three primary reasons why sort of C++ would be classified or regarded as an efficient, a fast language. And you can see them here. One of them is relevant to the point I want to make, but I'll show you the three reasons. Gives the programmer low-level control. You, as a programmer, have a lot of control over how your code gets to be executed. So you can optimize and precisely specify how it gets to be executed. That enables you to write something fast. It mostly avoids runtime checks, so there's less runtime checks than you would have in managed languages. And it avoids those runtime checks by assuming that the programmer is going to have written something that actually works properly. That's what makes it difficult. C++ is a compiled language. There are a number of extremely good compilers that will actually take the code that you write and put a wide range of optimizations or try to apply a wide range of optimization to it to get it running as fast as possible. So 3 reasons why C++ will be classified as a high performance language. Now, just because C++ could be classified as a high-performance language, it doesn't actually mean that the programs that you write will run fast in C++. This comes down to the programmer. This comes down to the algorithms that they use and how they actually code it. It is perfectly possible, as easy as any other language, to write highly inefficient code in C++. So just because C++ is a fast language doesn't mean you automatically or necessarily get it for free. And it ties in this key point then. So how does C++ help us then write faster programs? And it's that reason it mostly avoids runtime checks, assumes the programmer will have correctly written the code. In other words, if you want to write code in C++ that runs, it isn't buggy, you have to have a fairly detailed and precise understanding of the code that you've written and how it gets to be executed. And because you need that low level of understanding, it means that apart from writing things that actually will work, you're also more inclined to write things which are not going to be inefficient in the first place. So understanding it, because you need to do that understanding to get it running, also gives you the understanding to write it fast as well. You're not going to write something that is inefficient inadvertently. And that's the reason why we want to have a look at it. So C++11 enables programmers to avoid a lot of the housekeeping tasks, such as objects and memory management. It makes it more like Java and C#. And to be honest, if you actually are going to do real-world C++ programming, you should use C++11. However, because we're still in the process of learning languages, I do want to have a look at the low-level code that we have in the understanding bit. Do you disagree with this? Does this seem like a backward step to tech? That, well, why not sort of look at the C++11 standard? Why do we need to bother about this old style when it's moved on? Let me try to convince you. Here's a fragment of C++ code. It calculates a sum, basically. So we have a variable, a number, n, value 5,000, and we're creating an array of float values, 5,000 by 5,000. So you can sort of view this as a large one-dimensional array, or sort of a matrix, a square array. And then we've got 2 for loops, for x, 0 up to n, and for y, 0 up to n. And in the line 6, within the 2 for loops, we are adding up the values within that array. So we're adding up the sum and accumulating the value. So when we execute those 2 for loops, we will have gone through our array, accessed every single value within it, and added them up to get the total sum. And timed on a particular processor, it took 239.4 milliseconds. Okay, here's another fragment of code. Exact same data, exact same size of array, exact same calculation in terms of calculating the sum. All we're doing here is the changes in line 4 and 5. We are swapping around the order in which we're adding it up. So as opposed to doing x in the outer and y in the inner, we now have y in the outer and x in the inner. Both of these fragments of code perform exactly the same number of additions. Exactly. You access every single value within that array once. They will return exactly the same answer, so we don't have overflow. However, the version on the right, whenever we time that, it takes, for this processor, 79.5 milliseconds. It runs about 300% faster. And if you're sitting thinking, why is that the case? To understand why is it the case, you have to understand under the surface how the code gets to be executed. And there's a danger that at the level of Java and C#, that type of understanding, you never really need to get down to that level. But with C++, you do. Rather, with old-style C++, you do. And it's for that particular reason, because we want to be able to write code that is going to run 300% faster than some other way, we do want to have a look at old-style C++. So we have a bit of a summary in this. C++, I think it's a lovely language. It is regarded as a somewhat challenging language. We're going to explore old-style C++, and we're going to explore it to have a knowledge of it, yes, but primarily to make us better programmers, full stop, irrespective of the particular language that we're using.